Today's lecture then is on implicit differentiation, and the implicit differentiation is really just an application of the chain rule. So listed here is the chain rule. So if you're doing implicit differentiation, you're really doing the chain rule. All right, this is my first example. Okay, so we see what we have is an equation. Now again, from the definition of a function, I have to specify a domain and range set. So for any given x, I have to have a y value in order to have a function. So we're saying that there exists a neighborhood, some x and y region around this point, such that if you tell me an x value, there is a y value. I associate that y value with g of x. The unique feature here is that, of course, I can't simply write it out explicitly. I can't say g of x equals, for example, x squared. Of course, for this simple example, I can, but in general, I can't. So that's the issue. How do you handle that? And we'll talk about that in a number of our examples and develop this idea. So again, what we're given is an algebraic equation that determines this function g explicitly. Now in general, we're interested in more than this. In general, when you talk about the fundamental theorem of calculus, force equals mass times acceleration, for example, conservation of mass, momentum, and energy, you're going to have the function, the solution, also implicitly defined, but it won't be the solution of an algebraic equation like this. It'll be the solution of an equation like this, including derivatives, a differential equation, typically in x, y, z variables and time. So this is the starting point for all that, and that's why these are significant, and the approaches we're going to have and the ideas we're going to develop for this is also going to apply in the more general case that in fact you'll be interested in. So in general, what we have is we have this point here in the xy plane. We're going to have a neighborhood around this, an x and y set, such that it defines a function. And what we're looking for then is going to be the slope of the tangent line when x equals 2, or basically the linear approximation around this point. So in terms of the picture, you can see this is what we have in general. Here's our point. This is, for example, today, the state of affairs today, the weather today, right around this point. Now there exists a neighborhood around this point. Now generally speaking, I won't know how large this neighborhood is. However, it does exist, and notice it tells me there's an x range and a y range in this picture around this point. And what I'm really going to do, and generally I will not know, you can see there is a function. Again, the equation here is not a function. If I were to limit it to the top, to the positive y values, positive 0, of course I could have a function. But generally, of course, you won't know that. We'll have only a point, the present state of affairs. We know there's a neighborhood of which this function exists, and generally what we're going to do is approximate it by either a linear approximation or a Taylor polynomial. That's one approach to dealing with these problems. So our job will be to get, well, the slope of the tangent line so we can come up with a linear approximation. And of course you can see on this neighborhood locally, the tangent line, the linear approximation is good. If you want it to be better, you take a smaller neighborhood, and that'll be the idea. Or else if you want to keep this large neighborhood, use a second Taylor polynomial, third Taylor polynomial, and so forth. So that's where we're starting. So let's begin. Again, this is a very formulated way to do this. It's not random. It's not an accident how this happens. Again, I don't know if you don't need to write this down, but you should always think about this. I have a function rule defined. Now again, the dot 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 means I can't list it explicitly. Again, in this case I can, but generally speaking, you can't. In general, I've been listing the domain and range as separate sets, but in general what they'll be is they'll be contained in some neighborhood of the current point. So, for example, today, and we're trying to predict the weather tomorrow. So that's the idea here. So again, you're generally talking about a more sophisticated idea. We want the domain and the range to be in this neighborhood. Okay, so that's what we're talking about. The domain here is going to be this set of x values down here, and of course the ranges would be these y values. Now again, it's a fixed procedure, and it's not really harder to do implicit differentiation than write this function out explicitly and then take its derivative. That's not easy. This is not bad. I have functions of one variable. I can't take the derivative of x and y. What I really need to do is have everything as a function of x or x. Now, of course, if you're leaving y in there, you're just implicitly doing this in your head. I don't think that's a good idea, but you do what you want. Everything is a function of x, so now I can take derivatives, right? So I'm going to differentiate this. So just like we did before, I'm essentially taking the derivative of both sides. I mean, if I had f of x equals x squared, I'd take the derivative on the left, I'd take the derivative on the right, and it would be exactly the same thing. So this is just a generalization of what we've been doing. Now, when you look at this, again, you have to apply the rules of differentiation. What rules can you use? Of course, the derivative of a constant is going to be 0. Really, I take the 16 out, and then 1 is x to the 0 power. But okay, derivative of this. So the right-hand side is easy. If I look at the left-hand side, what is the only rule that applies? And the only rule that applies on the left-hand side is going to be the sum rule. Now, don't stress out about this. This will come out naturally, organically. There's no problem. It'll just work itself out without stress. So again, I'm going to use the sum rule, and I'm just going to break this down. Of course, it's always a matter of divide and conquer. Break it into an easier problem. If you can't see the step you need, it's either algebra or apply one of the rules. That's your only options. And again, the x squared isn't hard. We can just easily take care of that within the problem. And the derivative of 16, again, it's really take out the 16 and 1 is x to the 0 power, but okay, we can save the step. So what we need to work on is this term here. And again, I mean, don't stress out. Let's just break this off and deal with it. And it's quite common a term, so let's just look at it separately, right? I mean, there's no sense doing all this in one spot. Fold your paper in half, do this on the right-hand side. Now, what rule applies here? I mean, when you look through the list of rules on, for example, the crib sheet that I gave you, what can you do? I mean, the only rule that can possibly work here is going to be the chain rule. So if it's the chain rule, it has to be h, you don't have to use a notation, but in my notation, h equals f of g. So what is our function h going to be? H is going to be, of course, this function. And we're just going to then go through, set it up as a chain rule problem. So let h be this function, and we need to determine its derivative. And when you know it's a chain rule, automatically you know you have to find the functions f and g, right? So again, let's just look at it. H equals the composition of f and g. So we have to identify the function g, and we have to identify the function f. Now, the only new feature is that we usually have g of x equal to something. In this case, g of x is g of x. I mean, I don't know what it is explicitly. That's fine. Just relax. Let it go. Let the process work itself out. Don't get excited. Just let it go. Now we know y is g of x. So let's identify the function y, right? So our function of y is going to be y squared. So here we have it, right? F of y is y squared. Y equals g of x is, again, there is a function there. I just don't know how to write it down, we'll pretend in this case, explicitly, right? And that's fine. I mean, there's nothing, let's just the process work its way through. And again, it's never a bad thing to check that you've done this right. Remember, y is a placeholder. It's just an empty box, so we'll just substitute in the g of x goes in there, and you see that it works out, right? We just plug it back in, and there it is. So we know we made the correct choice for f. All right, once we have f and g, then the usual way is we need the derivatives, right? We need the derivative of f with respect to y. We need the derivative of g with respect to its variable x. So f of y is y squared. We just take its derivative. Now, again, this is pretty straightforward. We don't have to make a mountain out of this. G of x, I don't know what the rule is, but gx is the derivative of g of x. Fine, just let it go. With respect to Fy, I mean, again, it's just, you don't have to write all this out. You can do it in your head. I just want to show you that we are following the rules. If you had to use a chain rule in here or do something else, fine, just break it off. It's no big deal. On the other side, gx, I don't know what g of x is. I can't write it down, so it's not surprising I can't say any more here. Just fine. These are actually easier than standard chain rule problems. Just leave it alone. All right, so now we come to the usual chain rule. Now again, I'm not saying you have to write this out. You might just start out with the last line. That's fine. Here's my data up in the top right. This is all you have to have. You identified the function f of y is y squared, its derivative. G of x, I don't know. Gx, again, I don't know what it is explicitly, but I'm using the same format that we always use with the chain rule. And I'm just going to plug this data back in the chain rule. So g of x is g of x. I mean, gx is gx. I don't know what it is. Just leave it alone. Don't stress. It's actually no big deal. G of x, again, I don't know. Leave it alone. Now, fy, again, y is a placeholder. It's a box. Whatever goes in that box, right? We just substitute in the box. G of x goes in the box. So, right, just cut and paste. So that's it. So fy of g of x goes to g of x. We just plug that directly in here. So that's it. That's it. There's nothing more to say about this. Just leave it alone. Again, you can be stressing out, I don't know this and that. It'll work itself out. It's no problem whatsoever. It just comes out for free. So here's where we left the problem. Here's where we left off. On the right side of the page, for example, we calculated this, and we'll just substitute it back. Just substitute it back. No problem. Just substitute it back. And that's it. Leave it alone. All the calculus is done. You might want to clean up the algebra at this stage or something. I mean, you could divide by 2. I don't know. Who cares? It's just fine. All the calculus is done. If you want to do more algebra, that's fine. Okay, so what's the next thing we want to do? Well, we want to define the derivative when x is 2, or about this point, right? The slope of the tangent line in this point. So when we have a point like this, what does it mean? It means literally that x is 2, right? That's what the point means. And it means y is 2 square root of 3. And we know that, of course, generally, y is g of x. In this case, x is 2. So the value of y associated with x equals 2, this function is 2 times the square root of 3. I mean, it's that straightforward. Now, let's go back to the last equation that was highlighted. This is what we had. And we're just going to plug in the data from above. So again, it's always going to work like this, always. I'm going to just simply plug in my x equals 2, right? Everywhere you have an x is a box. Cut and paste 2 over that spot. And that's all I do in the slides, obviously. Now we do know g of 2 from up here. Notice I'm not mixing x's and y's, yada, yada. I don't want to get all crazy. G of 2 is that. It's straightforward. Just plug it in. And now I'll just solve for this quantity. Remember, this is a number. This is just simply now an algebraic equation. If you're uncomfortable with solving this for this number, replace this. Call this like a capital Z or something, or a Y or X or anything you want. Just solve this algebraic equation for this number. And you can always do it. Calculus, one of the reasons calculus is effective is because you can always do this. Always. This will always possible to solve this algebraic expression explicitly for this number. And it's just going to be algebra. So take your time. 2 times 2 is 4. This is 4 times all this. Now what I'll do is I'll throw all the numbers on the right side and just, right, and then I'll divide by this and it comes out here. Now I don't care about rationalizing the denominator. Just leave it alone. I mean, if you have to do it for the answer in the back of the book or somebody, whatever. I don't care. It's fine. Just leave it alone. So notice that's what I have. And that gives me the slope of the tangent line. Right? Change in y, change in x when x equals 2 is by definition the value of this function is 2. That's how we derived the derivative, right? By definition, the derivative was derived at the value when x is 2. This point is the slope of the tangent line. And we have that. So that's it. We answered that question. Of course, the next questions would be, what's the equation of the tangent line? And then more importantly, what's the linear approximation? So, of course, that's the next question. Now that we have the point and the slope, find the tangent line to the function. Now, again, I don't know what that function is explicitly. I know it exists in a neighborhood of this point, and we can plot a tangent line on that graph. So, again, the same way we've been doing this all along, you list your data. I have my point, right, that's given to you, and I have the change, right? I have the dynamics. This function is changing, change in y, change in x at this point, right? When it's a function, if I tell you x is 2, you know that this exists. So the dynamics, the slope of this, the tangent line at that point is this value we just found out. And again, how do you calculate the tangent line? Well, I mean, this should be a routine calculation. Y equals mx plus b, plug in your slope, right? Plug in your xy pair, and then do the algebra. This is a little messy. And again, I mean, unless you have to, I wouldn't get a comment. I would just leave it alone. You don't need to get fancy about it. This is just y equals mx plus b. Again, whatever. If you have to clean it up to meet the answer in the back of the book, fine. But for me, who cares? Just leave it alone. And then, of course, now, and that's the answer, that's the tangent line. And then we want to, of course, always turn it into the linear approximation. So find the linear approximation to this function around this point. And again, if that's your tangent line, that's your linear approximation, right? The rule is exactly the same. We replace y equals L of x. So we have a domain and a range. And again, these are global. These are everywhere. And if we look at the picture, that's exactly what we have. So again, I don't think this is any more difficult than if you solve this for, let's say, solve this for y up here and turned it into the function g of x and took its derivative. I think that would take more time or be more difficult than what we just did. Implicit differentiation is not harder. You may be more uncomfortable with it, but it's not really harder. So again, you can see, why deal with the function when you could just deal with the linear approximation? Again, if you're staying local to this neighborhood, the linear approximation is just, again, it's fairly easy to use. If I need more accuracy, I'll take a smaller neighborhood, or else I'll use a second Taylor polynomial or a third Taylor polynomial, and we'll look at that later. And this is one of the ways we deal with this. You either get all the data locally. Again, if I want the second Taylor polynomial, I need a second derivative, third derivatives for the third Taylor. You need more smoothness at the one point. But I can generate a function that's as good as this, and I can have it explicitly, and it's a polynomial. Or the second approach is I can use what we're going to do as the fundamental theorem of calculus later on. Those are the two approaches that you're going to use, and that really is the calculus. Again, these are the tools. These are the wrenches. But who cares? They're the tools. How you use it is this. If I want more accuracy, I'll take either a smaller neighborhood, or I'll use a higher Taylor polynomial, or I'll use the concept of the fundamental theorem of calculus. Those are the ways we do it. That's actually how we use calculus. So let's look at then another problem. Now, what I'd like you guys to do is work through this yourself. So at certain points, pause the video, try to work on it. If you make a mistake, that's fine. You learn by making mistakes, but I want you to dive in. The rules are either the algebraic rules, I have them listed on that crib sheet, or else the calculus rules, also listed on the crib sheet. That's it. That's the rules of the game. You do not need to reinvent the wheel. This will work exactly the same as the last problem and all of them. So again, let's work on this. We have a different equation, and again, you could probably solve this for y equals, yes, of course, to determine a function in the neighborhood here. And again, I want the slope of the tangent line when x equals 2, or the tangent line around this point. Okay, in terms of the picture, this is what we can see. Now, interesting, I generated this function g by using the fundamental theorem of calculus. I did this by we'll talk about how I did this later, the fundamental theorem. So I don't know this. I could probably in this case solve for it. But again, it's so easy to generate these kinds of solutions using packages like programs like Excel. It's just so easy. Doing other techniques, why am I going to waste my time? This is how we do it. But again, you can see, here's my point. I have a neighborhood here. Now, of course, the neighborhood could be bigger. But on this neighborhood, I can replace the function with the linear approximation. And you can see, again, it's pretty good. If I wanted a better approximation, I'd take a smaller neighborhood, or I'd take higher order Taylor polynomials. Or, like I said, I actually generated the solution using the numerical methods from the fundamental theorem of calculus. And that's another approach as well. So let me start again. You don't need to necessarily write this down, but you should think about it. Again, I do have a function defined in this neighborhood. There is a neighborhood of this point, right? Such that if I tell you the x value, you can calculate a y value from this equation, right? For every x value, there's one and only one y value associated with that. This is just a statement of that, right? So again, I just have a neighborhood that tells me the domain for me in this picture is just these x values, and the range is this y value. It just, there exists some neighborhood. You don't know how big it is. So that's what we have. Now, pause and just follow the previous steps and see if you can set up the problem, and then I'll start in a minute. Okay. Okay, so let me jump back in. Again, it's important that you try. The first thing I want to do is make everything have the variable x. I don't want to mix x and y's. If you are mixing x and y's from high school or something, it's just a placeholder for what I'm doing. Again, how many of these problems are you going to do in your life that you need to have shortcuts? I mean, I don't do this outside of a calculus class. I don't need it. So what I want is, I want the variable to be x. So again, this is what I have. Again, the next step will be differentiation. Now, if you haven't done this, again, pause the video and try and see to do it using those rules. Have a discipline in how you approach the problem. Again, what I see here easily is this is going to be easy, right? Power rule, 3x squared. So I'm not going to stress about that. If I look at the left side here, what's inside? What is the only possible rule I can use here? Now, of course, you could distribute this, whatever. I mean, it looks like the product rule, right? So it looks like I'm going to use the product rule here. And that's, in fact, what I did, right? I'm just going to use the product rule. So first times the derivative of this plus this times the derivative of this. So again, you're breaking the problem down into two easier problems. Now you can see this is pretty easy to deal with. This is pretty easy to deal with. This we may stress out but we'll come back to this later, right? So we'll come back in a minute. So again, I don't know if you need to put these steps in here. We all know 4 minus x derivative is minus 1, but again, I want to emphasize that there's always rules here. Whether you write them down or not, there are always rules. It's not a mystic experience. It's not, we're trying to do math, right? Derivative of the constant, again, it's take the 4 out, then it's 1. 1 is x times 0. Okay, the derivative of a constant is 0. Derivative x to the first power, right? And then this is this. So we're just really using the power rule here. All right, so notice, clean that up. The only thing left over the only thing left over at this point is this term, and we did this on in the previous example. But you might work it out yourself. Try again, right? What is this? You're going to use the chain rule. So again, give it a try. We did it in the previous example. You can go back and look at that. But it's a good time just to give it a try now and then check that you can do it from the previous, go back in the video, the previous slide. Okay, I'm going to write it down now because you could pause the video, right? So we had from the previous example that derivative of this using the chain rule is just this, and I'm just going to plug that right in. All the calculus is done at this point, right? All the calculus is completed. I mean, I'll clean it up. You have a minus sign here, so I'll just move that make it a minus sign, right? Again, minus 1 is the same as the minus sign here. So again, you could multiply this all out. Who cares? I mean, if you want to, that's fine. If you don't, whatever. So now I'm just simply going to take this expression, and just as we did before, plug in the data. Okay, so just as we did before, my data point was 2, 2. That tells me x is 2, tells me y is 2, but y is g of x. Here's the equation. So why don't you guys take a minute, pause the video, plug in the x value, plug in the g of 2 is 2, and see if you can solve it for gx of 2. And again, I'll give you a minute. Try to see if you can do it, and I'll do it in a minute. Okay, let me come back and let's try it again. So all I'm going to do is everywhere there's an x, I'm just literally going to cut and paste a 2. I mean, that's what you do. I just copied the line over and typed a 2 everywhere there's an x. Now we know that g of 2 is 2. So everywhere I have a g of 2, here and here, I'm just going to simply substitute 2. Right? G of 2 is 2. And now this is purely an algebraic. There's nothing to do, algebraic expression. I'm simply going to solve for this term. So just clean everything up, put the numbers on the right, get all the gx here, and then just clean it up, right? So 4 minus 2 is 2 times 4 times 2 is 4 times 2 is 8. 2 squared is 4, 12. 4 over here divided by 8, right? Put all the numbers on this side, and then you just have this divided by 8, and that's it. You have it, and that's the answer. So the slope of the tangent line, then, when x equals 2, change in y, change in x, the slope of the tangent line is 2. And that's it. Then obviously the next question will be, find the equation of the tangent line, find the linear approximation. So again, go ahead and pause and do that. That should not take more than 30 seconds. It should be so routine. Again, you don't need to think about it. It's a mechanical process. So try to do it yourself, pause the tape, just get it, do it 30 seconds, and then I'll continue in a minute when you're ready. Okay, so the question is, find the tangent line to this function defined implicitly by the equation in the neighborhood of this point. Again, write down, again, you have the data, but okay, explicitly I have a point, I have a slope, right? The tangent line is going to be y equals mx plus b. Plug in your tangent, right? Plug in the slope of your tangent line. Plug in your xy data, right? Solve for b. And that's it. Again, I don't know how much of this you want to include if you were taking a test. I suggest something, so if you make a dumb algebra mistake, that you can get partial credit. But again, you should decide. But my tangent line, that's the equation, right? It's pretty straightforward. And if I want to turn that into a linear approximation, so find the linear approximation to this function. Again, my tangent line is here, so my linear approximation is there. I mean, this is, again, you should be able to do these couple steps 30 seconds. It should be no trouble at all. And if I have my picture, again, that's what I have. It's not bad. You can see if the function isn't changing drastically, the linear approximation is pretty good. The neighborhood can be larger. Okay, here's another example. Again, this is, you can, I don't think, solve for this y equals or get a function g of x equals. So again, the issue is this equation defines a function, I'll call it g, in a neighborhood of the point 1, 1. And we wish to determine the slope of the tangent line around this point, right? When x equals 1, it's a function, so I know y equals 1. All right, the process is going to be exactly the same as we've done in the past two examples. So why don't you guys give that a try and then come back and compare it to me. Again, I want you guys to work it out. Try, work it out, see how it goes. Okay, let me jump in. Again, you can see we do have a function here, right? We do have a function in the neighborhood of this point. Again, I generated this by using the ideas of the fundamental theorem of calculus. But we clearly have a function in the neighborhood of this point, and we wish to determine the tangent line about that, right? Change the function, which I don't have an explicit rule for, but you can see it exists. So again, you should think about this. In the neighborhood of this point, I have a certain range of x values, right? Somewhere in the neighborhood of 1 and a certain y value, such that a function exists. Now again, I don't want x and y's in here. I want it all to be x's. So this is what I actually have, right? Everywhere there's a y, y equals g of x. So I'm going to replace this, the y's, with this. And now we're simply going to differentiate both sides, right? Just differentiate both sides. And when you look at it, you should be able to get an idea. Again, if you haven't tried here, pause the tape, jump in, make sure you give it a try. It has to be the rules of differentiation. You have to use those rules. So jump in. All right. If you look at the left, I'm thinking the sum rule here, right? The sum rule. And if you look at the right, again, what is the only rule that you can apply? Well, I guess you could take out the 2, right? Constant rule. Just take the 2 out. I mean, you could, I guess, use somehow the product rule. Just take out the 2. So on the left, I'm just going to use the sum rule, right? I'm just going to break this into the 2 pieces. And on the right, I guess I'm still working on the left here, right? X cubed is 3x squared. Okay, that's fine. I'll worry about this later. Right, worry about this later. On the right, again, you should always be thinking about taking out the constant rule first. I think it's the rule number 1 I have, but again, it's just don't use the quotient rule. It's first. The constant rule is an easier rule to use. It makes life easier. So just take out the constant. And now you can see what I have here. It's going to be the product rule, right? This is going to be the one function. This is the other function. And of course, that's what I have. So the 2 is out in front, and then I'll just use the product rule here, right? And I get this. Now, of course, the derivative of x is to the x to the first power, so that's pretty straightforward. Again, I don't need to make a mountain out of this, okay? It's just, I get it, derivative of x is 1, but I want you to understand, again, there are rules to every step we change. It's not a magic, it's not mysticism, it's not, right, it's a rule. All right, now let's look at this term, I think, right? What can you do with this? Well, again, by definition, and this is really the new feature of this problem, right? By definition, g goes in, right, to the operator, gx comes out, right? So that's the only possible thing I can do here, right? It's the only thing. And again, if you look at the tools in your toolbox, what else could you possibly do there? That's just simply the definition here. G goes in, gx comes out. All right, so everything is done except this term. And how are we going to do this? Well, exactly the same. The only possible rule that could apply here, right, the only possible rule we could use here is chain rule. So again, give this a shot if you haven't done it. Fold your paper in half, try it on the right. It's going to be chain rule. So we did g of x squared. This is going to be exactly the same, only replace the 2 with the 3 and follow it through. So again, I'll give you a minute to do this if you haven't done it, but jump in and try to do it. So pause and I'll come back in a minute. Okay, so let's look at it carefully. This is what I'm trying to compute. If I'm going to use the chain rule, right, it's going to have this format, right? So the function h is going to be g of x cubed. So let's set it up in a standard problem. Again, there's nothing new here. Standard problem. And if we're using chain rule, I have to find the functions f and g. If you're using chain rule, you are talking about composition of functions. One way or another, that's what you're talking about. So you have to identify the functions f and g, right? So h equals f of g equals, right, by definition, this is our particular function. G is, I don't know, I can't write it explicitly, that's fine, no problems. Y equals g of x, right? So my function of y is going to be y cubed. And again, this is calculus of a single variable. But notice the variable is different. G is a function of f, G is a function of x, f is a function of y. That's fine, there's no problems here. So now I need their derivatives. Again, it's not a bad idea to check, right, that you didn't make any mistakes with your functions. So y is really a placeholder, it's a box. G of x is in that box, so I just plug it in. And you can see if I plug it in over here, I get the function. So it's good. My choice of f is correct and everything. So again, you can do that in your head. It's no big deal. So now I have this function. I need its derivative, and I need this derivative for the chain rule, right? For the chain rule, I need fy and gx, right? So f of y is y cubed. G of x is, of course, g of x. I can't do anything with this. I don't know what the rule is here, so I'm certainly not going to know the rule here, but there is a function that exists. So again, y cubed, these are just a standard power rules. Again, you can do this in your head. I just want to point out that there are rules, and we're not making this up as we go. It's standard. But again, we get this table of data, just as we had with the regular chain rule, right? I have the function, its derivative, g and its derivative, and I have the chain rule. Every time you use the chain rule, again, it has to be composition of functions. I'm just going to plug the data we have into this rule, and that's it. So gx is gx. There's nothing I can say. Just leave it alone. G of x, okay, g is g. There's nothing I can say. Fy is this function. Again, y here is just a box. It's a placeholder, right? Whatever goes here gets cut and paste here. In this case, right, g is in there. So we just plug that in here, plug that in there, and that's what we have. I'll just replace it, and we're done. I mean, okay, I don't know this, I don't know gx, but it's fine. We'll just go through it, and it's fine. So I go back to where we left off. I left out some of this stuff, right? But this is the line we left off, where we left off, and I'll just simply replace what we had before. And you notice this calculation was almost exactly the same as what we did before. You start seeing it's all the same. There's not a lot of variation here. Once you do enough problems, work with me, try a few homework, work at the lab on Friday, you see it's all the same thing. We're done. There's no more calculus to be done here. If you want to clean it up, it's fine. You could factor out the threes, but I don't even care. I mean, it's done. Now, at this point, substitute in your data, right? At this point, we want to substitute the data. Our point is 1, 1, which says x is 1, y, which is g of 1, is 1. Here's the expression where we stopped, where we left off. So you take a moment, guys, plug that in, and solve for gx of 1. Okay, pause the tape and see if you can do it, and then I'll come back and do it. Okay, so what do we have? I'm just simply, once again, everywhere there's an x, I'm going to place a 1, right? Everywhere there's an x, I put a 1. Everywhere there's g of 1, I'm going to substitute 1. I mean, and then it's just an algebraic expression. If you're uncomfortable with solving for this, everywhere you have this, just place a giant x, a y, a z, something else. Just place, it's an algebraic expression, you can solve for this. What I like to do is just clean up the algebra, right? Clean up the algebra, right? Bring the 2 in. 1 times 1, of course, is 1. Distribute the 2, right? I just put all the g of x's on one side and put all the other garbage on the other side, right? And you get this, right? You'll have put this 3 on this side, so it's going to be 2 minus 3 is minus 1. You have 3gx here. Bring this over. It's going to be 3gx minus 2gx is gx. And it's always going to work like that. You can always solve it for gx. And again, maybe it's an algebraic issue. You know what? You have to practice the algebra. Everyone needs to practice algebra. But it is just algebra. So just take your time at that stage and do well. Now, of course, the obvious question is, once we have the derivative, the slope, right? Change in y, change in x. When x is 1 at this point, we can come up with the tangent line and the linear approximation. So pause, and why don't you guys calculate the tangent line linear approximation before you restart. Okay, So here's the tangent line problem. Find the tangent line to this function defined implicitly by this equation in the neighborhood of this point. So again, we have the data, right? We have a point, right? We have the point, and we calculated the slope from the last problem, right? And y equals mx plus b, right? Plug in your slope, plug in your xy data, and we'll just always solve for b. And then y equals this simple expression, it's a line. I mean, again, it doesn't have to be a mountain, and this should not take long. This is standard. You should be able to do this in 30 seconds. Once we have the equation, we can turn it into the linear approximation. I want a function here. If that's my equation, my function has the same rule here, but it's a function. And if we look at the picture, that's it. Again, I calculated this by using the fundamental theorem ideas. This is my tangent line. And again, you can see it's very accurate in this neighborhood. If you want more accuracy, smaller neighborhood, take your higher order Taylor polynomial, or use the fundamental theorem calculus. So that's pretty straightforward. Okay, now this one has a trig function, and that's the new feature. And in particular, this is how we actually, I'll show you, calculate this function. But let's just go through it and I'll talk about it after this example. So once again, this equation defines a function in the neighborhood of this point, right? So if you plug this in for x and this in for y, this satisfies this equation. And we want to replace this with a tangent line. In fact, we'd like to really replace this with a Taylor polynomial of some order because, well, you'll see later on. So again, you should try. It's straightforward. Just follow the procedures and you should be able to go all the way to the linear approximation here. So pause the tape and give this a shot. I'll start up again in a minute. Okay, now of course you can't really draw this picture, on the test. You could of course do it. I generated the actual solution, or at least the green line, by using the fundamental theorem, and this is the linear approximation. So again, this is not obvious what this function is or even how to define it, but again, in this neighborhood, my linear approximation is very, very good approximation. So we just follow the steps, right? There exists a function in this neighborhood. Again, I don't know how big it is and so forth and so on, but there is a neighborhood such that for every x value, you can solve for the y value. Now again, solving for the y value isn't so easy. I mean, for any x I give you, you have to solve the y value. How do you do that? I mean, this is one way. We could generate a linear approximation or a higher order Taylor polynomial or the fundamental theorem to generate that. But solving that is not a trivial matter, right? I mean, you might do it in a numerical methods class, how to solve these types of problems, but this is not a trivial exercise. So how do you get this? I picked 1/2 here. Suppose you pick 0.49. How would you pick a y value? This is a tough problem. It's a practical problem. So again, I know there's a function. I have a certain neighborhood where I know it exists. So here's my equation. I'm simply going to substitute y equals gx because I want x to be the variable, or at least there to be only a single variable, right? It's calculated, so a single variable. And then we'll take derivatives, again, of both sides. Again, this is easy, so we're not going to stress about this. This is x to the first power. Okay, it's 1. Again, you don't have to make a mountain out of this. So now we need to concentrate on this. So again, fold the paper in half and don't panic. The only rule that I can apply here is chain rule, right? Is chain rule. It's the only one that can work. This is not, again, sine of x. It's not. It's the only rule that can possibly apply here is the chain rule. So pause the tape, give it a shot. Remember, if it's the chain rule, you have to have composition of functions. You have to have functions, for example, h equals f of g, right? So pick your function f. Your function g is already g. Find their derivatives, plug into the chain rule formula. Give it a try. If you can't do it, fine, I'll do it in a minute. But see if you can do it. Follow the process. There is no free will here, right? There is no free will. You have no choices in what you can actually pick here. Okay, guys, I'll pause it and we'll get on that. Okay, let me jump in. This is what we have. right? And I want it to be chain rule, right? So I'm going to call the function h, and h equals f of g. So this is going to be my function h, right? My function h. And I want to find its derivative. So here's my function h. I want to find its derivative. If I'm using the chain rule, I don't have a choice. I need a function f and g. Again, whether you write these down explicitly, whether you do it in your head, whether you just memorize a formula, one way or another, you're doing the functions f and g. You don't have a choice. So h is a combination, is a composition of f and g. G, okay, again, the chain rule isn't harder. G is just going to be G. I don't know what it is. Fine. I don't know what it is. But I do know y is going to be g of x. And so up here, I'm going to have sine of y, and that tells me my function of y. Again, notice everything is a single variable, but that variable changes, right? G is a function of f, y equals g of x, and f is a function of y, sine y. And again, it's never a bad idea to check. F of y is sine y. Again, y is simply a placeholder, memory location, memory address, what's in there in the memory address. G of x goes in here, g of x goes in here, and so it checks out. Right? This is what I have. So I did make the correct choice for f. Okay, now if I need chain rule, right, I have the functions f and g, I need their derivatives, fy and gx, right? So f of y is sine y, g of x is g of x. I can't write it down. Again, it's the same. It's actually just easier than a regular derivative. And I'm going to replace f of y with sine, and the derivative of sine is cosine. So I have my table, right? I just don't have g of x and gx filled out, but I have my table, just as we did with chain rule problems. Again, over here we have the chain rule, and I'm just going to plug in the data. Again, you don't have to write all this out, but I always want you to understand, whenever you're using chain rule, you are using composition of functions. So I'm going to replace gx, just as we did with chain rule. Okay, in this case, there's nothing. G of x, again, there's nothing to put in here. But f of y, right, fy here is cosine y, so y is the placeholder, right? Y is the placeholder. Whatever goes in this box goes in this box. G of x goes in the box, right? And so we just replace. And that's it. There's nothing else we can do here. We just leave it alone. Plug it back in and it'll all work out. Again, it's not a very complicated process. I mean, on the right side of your paper, there should be maybe 6 lines. That's it. It's not, you don't have to make a mountain out of it. So this is where we left off, right? This is where we left off. We had the original equation where we replaced y with g of x. We took derivatives of both sides, and derivative of x is 1. We calculated this on the side. I'm just going to plug it in, and we're done. There's nothing else to say here. All the calculus is complete. We're done. At this point, we just want to substitute in the data and solve for gx. That's it. So again, give it a try. I'll pick it up in a minute and see if you can do it. Okay, coming back, here's my data point, which tells me x is 1/2 and y is pi over 6, but y is g of 1/2. Here's the equation we left off with, and we just plug in the data. X is 1/2, right? Everywhere there's an x, I plug in a 1/2, right? And g of 1/2 is pi over 6, right? I just plug that in there. And cosine of pi over 6 is square root of 3 over 2. And yes, you should know the basic trig ones, 30, 60, 90, 45. You should know the basic trig ones. I don't go too crazy with all the others, but you should know the basics. And we can just solve for this, just multiply by 2, divide by square root of 3, and we get that. And that's what we're looking for, the slope of the tangent line, change in y, change in x, when x is 1/2, i.e. at this point, right, is 2 over square root of 3. And then we do the tangent line and the linear approximation. So take a minute and try to write those down. That shouldn't take that much time. Should be quick about it, automatic. Give it a shot. Don't worry about cleaning up the numbers. Okay, give it a shot. Okay, the tangent line problem, find the tangent line to the function defined implicitly by the equation in the neighborhood of the point, okay? So my data, I have a point, and which I give, and I have the slope, which we calculated in the last example. Again, change in y, change in x. When x is 1/2, i.e. at this point, because it's a function, right? If I tell you x, there has to be a y value, which is the value of the function. Y equals mx plus b. Plug in slope, right? Plug in the x value, plug in the y value, and just clean it up. I mean, I don't care. It's about minus 1/20, right? Or you can leave it like this. Nobody cares, right? That's it, right? That's it. And then we can turn that into the linear approximation. So find the linear approximation to this function, right? If that's my tangent line, right, then the function is exactly the same, right? The rule's the same when I turn it into a functional format. Right, there's difference, right? An equation is different from a function. X goes in, right? That's your input. You have an output value here, right? That's not what an equation is. And if we draw the picture, that's what we have. Again, it's a very good approximation on this neighborhood. Again, I don't even have the function written here, right? I don't even have the function. I know one exists. But how would you calculate this? I mean, if you're a calculator, how would you calculate it if you need these values? Now, actually, they do have a symbol for this. It is a function, so you could call it y equals g of x. People want to give it a name, and that name is, in fact, the inverse sine, right? Put sine inverse over here, sine inverse here. That is that function. How would you define it? I mean, you just go to your calculator, you plug in an x value and a y, a value of the function comes out. How does the computer calculate it? Turn this into a Taylor series, right? Use the linear approximation. You can approximate this function, this is g of x, with this linear approximation. That's it. That's the approximation, and if you're going to be in this neighborhood around 1/2, that's pretty good without error. Right? You cannot write down what this function is explicitly. However, you could write a Taylor polynomial of high order to get as much accuracy as you want on a neighborhood. Right? That is a function. And I'm saying that, again, how would you know what its derivative is? In calculus 2, you'll see that it's this format. Right? But what do I mean, okay, that's fine. But I could just replace literally this by its Taylor polynomial. Right? We have the first Taylor polynomial right here, right? That's it. That's the first Taylor polynomial, right? X to the first power. You could go on and obtain the next polynomials and so forth. So that's how it's done. If I'm going to plug it in a calculator, I don't know for a fact, I'd plug it in as a Taylor polynomial to some order that meets, how accurate does your calculator go? 8 digits? Certainly it's easier than, well, how are you going to figure this out? So again, I'm pretty confident that that's how your calculator would do it. And if I was going to take the derivative, as you'll see in Calc 2, write out the Taylor polynomial and take its derivative. Or you could just, memorize more formulas. I don't know. All right, here's another example, right? Here's another example. Here's another equation. Again, I'm pushing a little bit of the trig functions here just to give us some practice. It defines a function, again, in this neighborhood. And I want the slope of the tangent line. Here's my picture. Again, I calculated the green line using the fundamental theorem of calculus. I just did it on Excel. It's so easy, 30 seconds, done. Here's the linear approximation. And again, I don't know what this function is explicitly, right? I don't know what it is. But it's a pretty good guess. And if I want more accuracy, I'll use a Taylor polynomial. So once again, why don't you guys take a minute and see if you can calculate this and see how it goes. Pause and then come back and check with me. I'll start up again in a moment. Okay, as usual, there is a function. I can't write it out explicitly, and in fact, this is always the case. When are you ever going to have a function you can write out explicitly? I know it exists, and it's going to exist in this neighborhood. I don't know how large or small this neighborhood is. There's some x values around 2, some y values around pi over 3, right, around 1/3, around 1, I guess is what this is. So there is a neighborhood on which this function exists. Standard, right, I'm simply going to replace the y with g of x because I want everything to be a function of a single variable, right, single variable. And now I'll differentiate both sides. Again, just don't get excited. Do the easy things first. Derivative of constant is 0. Of course, 1 is x to the 0 power rule. If I look at this side, the only rule that can work is going to be the product rule, right? So we're just going to plug stuff in. This is the product rule here, right? So it's a product rule. This is, again, x to the first. To do the easy stuff, x to the first power, I'll just use the power rule here, right? X to the first power, derivative of x is 1. Derivative of x to the 0 is 0. Nothing to do here. This is out. So this is what I have to concentrate on, right? So let's fold the paper in half and do that separately. Now, when you look at that, the only rule, again, you have no free will here. No free will, right? Fate, free will. You have no free will. It's the chain rule. If it's the chain rule, then again, you have no choice. You have to identify a function f and g, take their derivatives, plug into the chain rule formula. So pause and give that a shot, and then again, I'll do that in a moment. But again, it's going to be a template. Everything is going to follow the same way. Okay, good luck. Give it a shot. Okay, coming back. Let's just, again, on the side of the page, if I'm going to use a chain rule, I like to call it h equals function f of g, but again, it's your discretion. My function h is going to be cosine of g, right? Cosine of g. And then we set it up as a chain rule problem. This is h. I want to find its derivative. If I'm going to use a chain rule, then I have to identify the function f and g. Again, you could just memorize formulas, but in choosing the formula, you made that decision. H is the composition of f and g, right? And it equals cosine gx, so I'll take gx to be gx. I mean, I don't know what it is explicitly, that's fine, but this is the same as we did with chain rule. Y equals gx, g of x, right? Y equals g of x. So that's y. And then my function of y is cosine y. Again, it just follows. Sometimes you have a choice. Most of the time, you actually don't have any choice. So I did guess my function f of y and, of course, gx. And you know, it's not a bad idea, again, to check. F of y is cosine, y is a placeholder, it's a box, right? It's a memory location. G of x is what's in that location. I just plug it directly in, and then I'll substitute this back. And then check, and that's right. Again, so I made the correct choices. Now, once I have the function f and g, I take their derivatives, right? From the chain rule, I need the derivative of f, I need the derivative of g. Again, the variables are different, but it's fine. It just works out naturally, right? F of y is cosine y. I need its derivative. G of x, I can't write it out, so I can't write out what gx is. Let's just do this side. I'll plug in cosine in here. The derivative of cosine is minus sine. And that's it. I mean, it's not, shouldn't be a big deal. Again, no single step you should be working that hard. If you are, I don't know, you're not putting in steps. Fight smarter, not harder. The problems can get longer, but not really, it's not hard. So here's my table of data. I have f of y, cosine, right? Cosine y. G of x, I don't know. The derivative here, f of y, is minus sine y. Gx, again, I don't know. Here's the chain rule, right? You're always talking about composition of functions if you're using the chain rule. And again, that's why I write this out. It's always composition. And again, we're going to follow the same rule process we use with chain rule. Again, if you're writing it on your notes, I don't know if you really need to do that, but I just want to emphasize that. G of x, I can't do anything, but it's gx. G of x, again, nothing. Now here's where you have a step. Fy of y is minus sine y, right? Y is the placeholder, right? It's a placeholder. And so we're going to plug g of x into that box, And that's what we have. Now we'll just take our result and plug it back into the original chain rule, and we're done, right? That's it. So we'll take this now and plug this back into where we left off. Okay, we left off here. We calculated this on, let's say, the right side of the page. And I just plug it in. And again, the calculus is done. You can clean up the algebra, like I put the minus sign out. That's fine. I don't know what a big deal it is. And now we'll just plug in the numbers. So again, take a minute, plug in the numbers, and then solve for gx. I'll pause the tape. I'll come back in a moment and take a look at that. Okay, let's take a look. Here's my data. X is 2, y is pi over 3, but more importantly, y is g of 2. Here's where we left off. Again, we're just going to plug the data in, plug in the x. Everywhere there's an x, I place a 2, right? G of 2 then is pi over 3, so everywhere I have g of 2, I plug in a pi over 3, right? Now, okay, these are numbers, and then I can solve for this. So sine of pi over 3 is square root of 3 over 2. Cosine pi over 3 is 1/2. And notice I'll just put this stuff on this side and divide, and I get that. Again, it's worth practicing the algebra. That's, of course, everyone needs practice. Don't be intimidated. We all need practice. Just give it a shot. So once more, I have the slope of the tangent line, right? Change in y, change in x, when x equals 2, or at this point 2 pi over 3, it's a function. By definition, it's this derivative, it's this number. And then the next question, of course, is find the tangent line, find the linear approximation. So I'll pause, and you guys give that a shot, pause the tape, give that a shot, and then we can compare. Again, it should be very quick. Give it a shot. Okay, this is what we have. Find the tangent line to this function. It's defined implicitly by this equation in the neighborhood of this point. So we have our data, right? There's our point. There's our slope, which we got from the last example. Y equals mx plus b, right? I'll plug in the slope and then the xy data, the slope, and then the xy data. And again, it's just algebra. Don't be intimidated. I don't know. You can practice, get a comment. I don't know, whatever you want. I don't really care. It's just this. I mean, it's just y equals mx plus b. This is a number. This is a number. Who cares? And then we can turn it into a linear approximation. That's the tangent line, right? And then as a function, right? Again, this is an equation of two variables. This is a function of one variable. We have the same rule. And again, if we look at the picture, it's a pretty good approximation. Again, do you know what this function y is? In fact, symbolically, you can call it something, right? If you have this, you really have this inverse cosine, so your function is really the inverse cosine 1 over x. But again, how would you calculate this for putting in an x? If you put in an x value, you have to go back and solve this. Or you can replace this by tangent line, by its second Taylor polynomial, by its third Taylor polynomial. And that's much easier, and that's in fact what we often do. Because how do you actually calculate the inverse cosine of 1 over x, right? And again, in Calc 2, you'll memorize a formula, whatever. But again, replace it with a Taylor polynomial. That's what I think. And that's what we do. All right. So here's another more complicated problem. So again, let's pause. Why don't you guys take a moment and try to work this out? So again, the equations are getting more complicated. But if you're putting in the steps, the problem's not harder, right? The problem should not be harder. So let me pause. You guys jump in and give it a shot. Okay, let's begin again. Again, you have this equation defines a function in this neighborhood. I mean, I'm sure you can't write down what this function would be explicitly. As a Taylor polynomial approximation, of course you could. We want to determine the slope of a tangent line here. Again, I drew the picture. I got the solution, the green one, by using the fundamental theorem of calculus. And this is the tangent line. And you can see it's very good in this neighborhood. This is not a function that changes extremely quickly. And the steps will be the same, right? There is a function in this neighborhood. This should be 0 pi over 3. I'd probably just cut and paste it or something, but okay, that's a typo. But in a neighborhood of this point, and again, I have a certain domain and a certain range of y values, and there's a function, you can see it here, I just can't write it down explicitly. Okay, so we have the algebraic expression, okay, the trigonometry, trig functions in there. I'm going to simply replace y with g of x. So this is a function. All this is a function of a single variable. And then we proceed, right? Again, take derivatives of both sides and just do one thing at a time. It has to be either the algebraic rules or it has to be the calculus rules. There's no other choice. Here we can see the derivative of 1 is going to be 0, so this side is going to be easy. On this side, what do I have? You can look at it. You can see you're going to have a sum rule. It's going to break it into the 2. And then again, okay, let's just do one step at a time. Sum rule here. Now, this is fine. Derivative sine is cosine. It's notice sine of x. Sine of derivative sine is cosine. Derivative 1 is 0. Now, let's concentrate on this. There's only one rule that we can apply to this function, and we'll take out the constant. Right? And now we have this. Okay, okay. I forgot I would take. Okay, let's do the easy stuff now. Keep working on the easy stuff. Derivative of 1 is 0. All right. 1 is x to the 0 power. Derivative of sine, I'm guessing I did that next, cosine. And now we can just concentrate on this piece. Okay, don't stress about it. Just don't stress. It's left. Fold your paper in half. Let's work on the right side and look at it. Now, when you look at this, again, the only possibility here, right, it's not just cosine x, right? It's cosine of all this stuff. So the only possible rule that we can use here is chain rule. And if you're going to use a chain rule, you have to identify, H is a composition of, say, f and g, in my notation I've been using. You have to identify the functions f and g. So jump in. This is a little harder. And there's a little nuance to this. That's why I picked this problem. Jump in and see if you can do this. But irrespective, try. And then I'll pause the tape and I'll start up in a minute. Okay, this is what we have. It's got to be the chain rule. Now you'll see why I'm going to call it H capital, right? I mean, this is one way you can get around these little things. I'm going to, instead of just calling it a small h, right? So I'm going to call this a capital H, and I can see in a minute. So in standard form, let h be this. We need to determine its derivative. Again, you could call it whatever you want. I mean, whatever. So I'm going to call these functions, it should be h equals f of g. So I have a typo here. I see f of g. And see, I fixed it here. Okay, so h equals f of g. So what are we going to take g to be? Take that, well, 2g. So that's going to be my y. And so my f of y is going to be cosine. So what am I going to have? I'm going to have f of y equals cosine y. And you see, this is why I took capital letters. This capital G is going to be 2 times g. Now, you could have taken g to be, capital G to be g, and then your other function would be cosine 2y. And you'd get exactly the same answer in that case. So that was some choice. You could have taken g to be g, and then this would have been cosine of 2y. But you'd still get exactly the same answer. So I just took this. And again, you can check. F of y is cosine 1, right? Y is a box. Capital G goes in here, but g equals 2g. So it all works out. It's correct, right? We made the correct choice. But again, you could have, it just took g to be g and had the 2 over here. It's fine too. So I need the derivatives, right? If I have the function f, I need its derivative fy, and I need g derivative gx. So f of y is cosine. g of x is 2gx, right? So derivative of cosine is going to be minus sine. The derivative of g, okay, it's going to be 2gx. And again, don't panic. What is the only rule you can use here? Take out the 2, right? Just take out the 2. And derivative of gx is gx. I mean, you can't simply do anything else. Leave it alone. There's no reason to make a big deal about it. But it is a different nuance. But what I want you to do is trust your instincts. Just push the problem forward without making up your own rules. Just push the problem. You learn by doing it. Again, you develop that confidence. There's no gimmicks or tricks. You have certain tools. Just apply them. Just push it, push it, push it. Here's the chain rule. Again, this is just to remind you you're always talking about composition of functions, right? You can't do chain rule without it. I'm just going to substitute in the data. The data's up here. So gx is going to be, right, 2gx. And gx is going to be 2gx here, right? So f of y is minus sine y. Y is a placeholder. Again, don't stress. Whatever goes in here, just cut and paste. And I'll take now this result back and plug it in over here. And you're good to go. I mean, you know, you can clean up the algebra. I put the 2 up here. Again, it doesn't make a big difference. And that's it. Again, it does have a little bit of a nuance to it. But, I mean, we've done pretty much everything we can do here, to be honest. And then we come back. This is where we left off, right? This is where we left off originally. Now, this work hopefully is on the side of the page. We'll just plug it right in, right? We have this derivative equals this. Just plug it in. Everything is modular, right? You should be not working it all in one line. Just, it's meant to be developed in pieces. Just plug it in. It's just, think of it as modular. Again, you're just taking this box, plugging it into this slot. And you can clean up the algebra. You have a minus 2, a 2 here. I don't know. Whatever. It doesn't make a big difference if you do or don't. And that's it. There's nothing else. There's no more calculus to be done. Again, this is it. You're done. I mean, don't make a big deal out of it. Okay, now at this point, plug in your data. You have your x and y data. Now let's take a look. You have, this is your x value, that's your y. Here's where we left off. Plug in your x and y values and solve for gx. And again, you can always do this. It's done the same every problem. So pause the tape, give it a shot, and then I'll come back. Start me up again. Okay, so here's your x value. Everywhere there's an x, I'm simply going to replace it with a 0. No big deal. Everywhere there's now a g of 0, I'm going to replace with pi over 3. Again, it doesn't have to be a big deal. Now you have to figure out what sine of 2/3 pi, I don't know, okay, whatever. But it's it. Cosine of 0 is 1. Sine of 2 pi over 3 is square root of 3 over 2. Put all your numbers on the one side, divide it out, and you can always solve for gx, right? You can always solve for this number. And that's it. And you're done. By definition, this is the slope of the tangent line, right? That's how we derive this function. Change in y, change in x, right? When x is 0, or at this point, and it equals 1 over 2 or square root of 3. 1 over 2 square root of 3. 2 times, 2 times square root of 3. Now find the tangent line, find the linear approximation again. It should be automatic. Don't take 5 minutes to just do it, 30 seconds. So pause the tape, give it a go. Okay, so here's the problem. Find the tangent line. Here's your data. There's your point. There's your slope. Right? Y equals mx plus b. Notice it's always the same. Always the same. Always the same. Plug in your slope. Plug in your data. Right? Clean it up. Again, it's a messy number. It's about a half. I mean, you should learn to think in these terms. I mean, who cares? It's about a half. So that's your equation of your tangent line. And then the next question is the linear approximation, right? And if your tangent line is this, your linear approximation is that. Now again, I don't know what this function would be. I mean, what would the function be? That's complicated. But as you can see, I don't know. I don't have to worry about all this. For all intent and purposes, if I can accept some small degree of error on this neighborhood, you can see this gives you a function. You plug in the x, you get the function out. Again, if you were to try to figure this out, there's going to be error associated with that as well. I mean, that's not an easy proposition. So I really have the function. And you could see I could take a much bigger neighborhood if I wanted, depending on your accuracy. So again, I can't really write down what this function is. But for all intent and purposes, if I can accept a little error on this neighborhood, that's what it looks like. And again, this is how we use calculus. Calculus is not the derivative of these things. Calculus is obtaining this linear approximation, which I'm now going to use because I don't have the function. It's all about fighting smarter, not harder. This is how we use it. Now, this is a variation on this. I picked a relatively straightforward equation, but what we're going to do is we're going to do the linear approximation, which is the same as it's always been. But in order to obtain a second Taylor polynomial, and this is what's new, and you're going to have this on the test. This is going to be the thing. If you have good technique, you can do this. You're going to take the second Taylor polynomial, so we're going to need the second derivative. So we need the first derivative for the first Taylor polynomial. We'll need the second derivative for the second Taylor polynomial. So the first part works exactly the same. So why don't you pause it and get the linear approximation. It'll work exactly the same as it's always done. Again, pause the tape and come back and check with me. But you should be able to do this. Okay, here we go. Again, here's my function. And again, I generated this using the fundamental theorem of calculus, and we'll talk about that when we get there. Again, you don't generally know what this is in the neighborhood of this point. And again, for the linear approximation, right, there is a function in the neighborhood of this point. Okay, here's my equation. I'm going to replace y everywhere with g of x because I want a function of only one variable. Again, it's just good technique. We do every problem the same. I'll take derivatives of both sides. Again, don't panic about this. The derivative of 1, 0. If you look on this side, I'm going to have the sum rule twice, right? And then we'll worry about the next step when we get there. So I'm going to break this down twice, right? This is easy, 2x. If I look at this, again, don't panic. Looks like it's going to be a product rule. We'll worry about this later, and this is going to be derivative of a constant 0. I did the product rule here. Again, you could do different steps. I mean, honestly, maybe take the easy ones out first. I don't know why I did this particular order. You can do it, you know. And then I guess because I want to do the power all at once, so derivative of x squared is 2x, right? The derivative of x to the first power is 1. Derivative of x to the 0 power is 0. So all that's done. Notice the derivative of gx, ddx, g of x, gx comes out. And then the only thing left over is this term, right? This term. And we did that in the first example, right? We did that in the first example. You can try it, but we did that in the first example. And so there it is. All the calculus is completed, right? All the calculus is completed. So now we want to evaluate that at the data point, right? Now hold on to this line. Hold on to this line because we're going to pick this up when we do start the second derivative. Right? We're going to pick this up when we start. So just hold this. That's fine. Just hold it. We'll come back. But this is where we left off. This is my point, right? X is 1. Y is minus 1. Or really more importantly, g of 1 is minus 1. Here's that equation again. Plug in the xy data. Again, if you haven't done it, pause and do it. So I'm going to plug in the x value. Everywhere there's an x, I'm going to simply just cut and paste the 1 in there, right? I didn't get the blue here, but anyway. G of 1 is going to be minus 1. So everywhere there's g of 1, I'm simply going to replace that. Right? And now you can always solve for gx of 1. So put everything that isn't gx of 1 on the right side. and just combine the gx's. Again, if you're uncomfortable with this, replace this term with a giant X, a giant A, or something else. This is just an algebraic expression. Just be patient. So 2 times 1 is 2. I just clean this up a little bit, right? You can see. Just, I don't know, take the 2, or I don't know how to do it. Take the numbers on one side and gx on the other side, right? You can put the gx's on, put all the gx's on the left side, put all the numbers on the right, whatever, just, and it solves for this. And again, that by definition is the slope of the tangent line, changing y, right? Change in x. This is to remind you, right? Delta y, delta x. When x equals 1, it's a function. So if there's an x is 1, I have a point, and that point gives you the value of the function. That's how we constructed functions. And that's it. So you can come up with the tangent line, right? Do it. You pause and do it. Right? Here's your point. Here's your data. Your point, the slope. Y equals mx plus b. Again, it's the same slides over and over again, and you should see it. This is automatic, right? Tangent is 1. The data is 1 minus 1, so my intercept, and then y equals mx plus b. And then you can have your linear approximation. If that's my tangent line, then that's my linear approximation. Again, it's a function, right? This is an equation of 2 variables. This is a function, right? Think of your function as a class. You're inputting data, and then you have an output, right? Your input, your output, your output. So, and if I, okay, now before I draw the picture there, let's look at the other problem, the second Taylor polynomial. So how do we do that? I need the second derivative, right? So for the second Taylor polynomial, and this is why this is important. Notice my function, if I'm going to get the second derivative, you input the first derivative, right? You input the first derivative. So all I know is that my first derivative is going to be defined in that neighborhood. Now look, we're going to proceed exactly the same. Before, we had this, right? This is what we had before, right? This is where we left off. This is how we put in the data for this. Now, if I want to obtain the second derivative, how do I do it? Gx goes in and gxx comes out, right? Gx goes into the derivative, gxx comes out. All I'm going to do is apply the operator ddx, the derivative operator, differentiation, to this equation. Sorry. So I'm just simply, where I left off here, I'm going to apply the derivative operator, right, to this. And why? Because you can see when I get to here, the derivative of the first derivative is going to give me the second derivative. And this is going to proceed exactly as we did before. To derivative of 0, it's not because it's 0. 0 is a constant, right? 0 is a constant. It's 0 times x to the 0 power. So the 0 comes out in front. X to the 0 power is 1. Derivative of a constant is 0. And here, I'm going to use the sum rule, right, on all this. So I'll take care of that later. I use the sum rule. Now again, don't panic. Do the easiest things first. Maybe just zero that out. If you look at this term, I'm thinking I can take the 2 out, right? It's a constant. Take the 2 out. And if I look at this term, product rule, just do it. You don't have to, again, you don't have to make a meal out of it. It's the product rule. You can see why I'm uncomfortable with it. I don't know what to do with this. It's fine. Apply the rules and have confidence in what you're doing. You know, my yellow box slipped over, but it's going to be the first times the derivative of the second plus the second term, right, times the derivative of the first. This is the same. I think I took the constant out over here. Right, I took the constants out. It's different on the Mac and the PC, I think. I did it on one and the other one, even though you do a PDF. But anyway, so don't panic about it. It's just, again, go back here. I'll take out the 2. Over here, I'll take out the 2. Of course, the derivative of this is going to be gx, right? That's easy. if I look at this, it's gone. You can worry, say, I don't know what to do with it. Just do the rules, have confidence. This is just going to be the product rule. And that's what we did all down here. Now we can look at, I don't know what I did. I can look at this one. The derivative of x is 1. So let's just look at it. Oh, I did the product rule over on this piece. Right? First times the derivative of second. Second one, derivative of first. Just a product rule. Okay. And now I just took care of the basic ones. Derivative of 0 is 0. Derivative of x is 1. Derivative of x is 1. Again, you could do different steps, a different order, but I'm always using the certain rules. Now again, let's look at it. The derivative of g is gx. Remember, g of x goes in, gx of x comes out. That's just a definition. Here, if gx goes into the derivative operator, gxx comes out, just by our definition of notation. G goes in, gx comes out. If gx goes in, gxx comes out. And that's what we have. If g goes into the differential operator, gx comes out. If gx goes in, gxx comes out. And that's it. All the calculus is done. And now we apply the data to this. And this is what's remarkable. Right? This is the equation. And if we wanted the third derivative, we just take the derivative of this. Now let's go up and see. Here's our data point. Right? We had x is 1. We had the point 1 minus 1. That says x is 1. Y is minus 1 in G1. But remember from the linear approximation part A, we also found out Gx of 1 is 1. So now this is our expression, and we'll do it exactly the same way. Plug in x is 1 everywhere. X is 1, right? X is 1. Now we also know that g of 1 is minus 1, right? G of 1, everywhere there's a g of 1 is minus 1. But we also know now, for a third step, we know g of x of 1 is 1. So everywhere I have a gx of 1, I put a 1. And you see the only thing left over is gxx. Oh, that should have been a 1, right? That should have been a 1. And so if we solve it, right, it's just algebra. We have gxx of 1 is 6. And that gives us, again, the second derivative, right? I explained this notation before. It's d dx of d dx. So the second derivative of 1 is 6. So now, if we want to find the second Taylor polynomial, this is our data, right? X equals, right, the point A is 1. G of 1 is minus 1. Gx of 1 is 1. Gx of 1 is 6. Our Taylor polynomial formula is this, right? Everything is around 1. And we just substitute in our data, right? We have g of 1 from here, gx of 1 here, and gx, and we just simply substitute in all the data, right? G of 1 is minus 1, gx of 1 is 1, and gxx of 1 is 6. And if you clean this up, it's just a polynomial. That's remarkable. I mean, there is a function here that I can't write out. I mean, maybe you could, I don't know, whatever. But there's a function, but for all intent and purposes, it's as simple as this polynomial. Here's the picture. Here's that function, and again, I generated this green line using the fundamental theorem of calculus approach. I did it with Excel in 30 seconds. Notice here's the linear approximation. It's pretty good. Again, we're comparing it to the green line. And on this neighborhood, it's pretty good. You can see there's a little error here, a little error here. But notice the second Taylor polynomial. Look, it's very good on this neighborhood. In fact, you could extend this neighborhood down here a little more. But you can see this second Taylor polynomial is excellent. Understand this. I don't know what this function is explicitly. I cannot write it out. But for all intent and purposes, if I limit myself from being global to having a neighborhood, and accepting some degree of error, this, whatever this function is this polynomial. How easy is that? If I want to take its derivative as a polynomial. If I want to integrate it, whatever. For all intent and purposes, this function, which I cannot write out explicitly, is simply a second order polynomial. If I want more accuracy or a larger neighborhood, take the third derivative and make the third Taylor polynomial. This is how we actually use calculus. This is what's important. The derivative of sinus, cosine, I don't really care. This, replacing the function that I can't even write out with a quadratic second order polynomial, that's what's very important. That's what we use it for. That's how you use calculus. That's how you could think. Okay, that's the last example. So try some homework, try the problems in the lab, try some homework, see if you're comfortable with it. So these are the type of questions you should expect on the exam. Any of these kinds of things. And if again, you should be able to do it. It shouldn't take 10 minutes per problem. So good luck with that. And if you have any questions, let us know.